Namaskar students. In this video, we will discuss about gamma distribution. We will be finding the moment generating function for the gamma distribution. Firstly, we will be discussing its probability density function. Then we will be discussing its moment generating function. From moment generating function, we will be evaluating its first two moments about origin. And with the help of those moments, we will be finding the mean and variance of gamma distribution. So here we have a continuous random variable x. This random variable x is said to have gamma distribution with two parameters. Here we have two parameters, lambda and a, and both of these parameters, they are greater than 0. So if x has gamma distribution with these two parameters, lambda and a, then its PDF probability density function is given by this function f. F is non-zero if x is greater than equal to 0, and otherwise it is equal to 0. This function is defined as a raised to power lambda, where a and lambda, these are the parameters which are greater than 0. Then we have e raised to power minus ax, x raised to power lambda minus 1, and is divided by gamma of lambda. So very easily we can verify that this given function, it is a PDF, it is integrable, it is non-negative, and if we integrate this function from minus infinity to infinity, then we will be getting here 1. When we will be integrating this function, then we will be using here the concept of gamma function, and with the help of gamma function, we can very easily verify that this integral is 1. Now let us come to its moment generating function. As we know that the moment generating function of any random variable, its notation is this one. We are finding here the moment generating function of a random variable x, which has a gamma distribution with two parameters lambda and a. This is given by the expectation of e raised to power tx. Now here, when we will be finding this expectation, it will be given by the integral, and the limits we have from minus infinity to infinity, e raised to power tx, and then we need here this PDF of gamma distribution. Here, this PDF is non-zero for x greater than equal to 0. So this interval, this domain of integration, it will reduce from 0 to infinity. It will be e raised to power tx, and let us put here the PDF. Let us use the definition of probability density function, which is a raised to power lambda, e raised to power minus ax, x raised to power lambda minus 1, and this divided by gamma of lambda, and we have to integrate this with respect to x. Now let us take here the constant terms outside. Here this a raised to power lambda, this is constant, so let us take it outside, and this in the denominator we have gamma of lambda, so let us take this also outside. So we are left here with e raised to power minus ax, e raised to power tx, and x raised to power lambda minus 1 dx. Let us integrate it. Let us collect the terms 0 to infinity. We have here e raised to power minus a minus t x and x raised to power lambda minus 1 dx. Let us consider here the substitution. Consider a minus t as a new variable, say y, So this will give us, here we have this x also. So the substitution will be, consider this a minus t, this a minus tx, this product a minus tx as y. Now let us try to find out here the relation between dx and dy. So what we will get here, we will get here that a minus t, when we'll be differentiating both sides with respect to x, will be this. Now let us convert this integral in terms of y as per the substitution. We get that the moment generating function, whose notation is this one, this is, we have this a raised to power lambda is divided by gamma of lambda, and in this integral, when we have used this substitution, the limits will be same, the same limits, 0 to infinity, no change in the limits. E raised to power, this will become minus y, and x is y upon a minus t, and this raised to power lambda minus 1. And if we check for dx, dx is dy upon a minus t. Now let us again take here the terms which are constant, which are free from y outside this integral. So this 1 upon a minus t, this whole raised to power lambda. We have taken it outside, and we are left now with e raised to power minus y and y raised to power lambda minus 1 dy. Now we have here this integral. This is gamma function, the definition of gamma function. So here we have y raised to power lambda minus 1. So this is a gamma of lambda. So it becomes a raised to power lambda, a minus t raised to power lambda. If we simplify it further, if we take this a, which is present in the denominator, common, then we will be having a raised to power lambda 1 minus t by a, this whole raised to power lambda. So we are getting here the moment generating function as 1 minus t upon a, this raised to power minus lambda. So this is the moment generating function. Now we will be finding the series for this moment generating function. So if we find out the series will be 1, then we have minus lambda, then we have minus t by a. The next term will be minus lambda, then minus lambda minus 1, 2 factorial, and minus t by a raised to power 2. This will go up to infinity. Now, if we simplify the series, we have lambda by a t, we have lambda plus 1 upon 2 factorial t square upon a square, and this will go up to infinity. Now we have the series for the moment generating function. So for finding the first moment about origin, we need coefficient of t in moment generating function. And the coefficient of t in the moment generating function, we can see here that this is lambda by a. And mu2 dash is the coefficient of t square upon 2 factorial in the movement generating function. And if we see here the coefficient of t square upon 2 factorial, then that coefficient is lambda plus 1 upon a square. Now, with the help of these two movements, these two first and second movements about origin, we can find out the mean and variance. We know mean is given by mu1 dash, so the mean will be lambda by a. Variance of random variable x, this is the second central movement, which is mu2, and this mu2 is written as mu2 dash minus mu1 dash whole square. So if we put here mu2 dash, which is lambda plus 1 upon a square, and we put here mu1 dash, which is lambda by a, we have here the square of lambda by a. And if we simplify it, we will be getting this as lambda square plus lambda minus lambda square upon a square. It will simplify to lambda upon a square. So if we talk about the mean for the gamma distribution is lambda by a, where lambda and a are the parameters, they are greater than 0. And if we talk about the variance of gamma distribution, then the variance is coming as lambda upon a square. So here, with the help of movement generating function, we have evaluated these two constants, mean and variance, for a random variable having gamma distribution with two parameters, which are lambda and a. Thank you. Have a nice day.